Alright, let's get started. Alright, so your assignment is out. Due Thursday as usual, Thursday and Friday. Then number 6 will come out, and then the week after that there'll be a midterm. So the midterm is March 1st, which is 2 weeks from Thursday. Are there any questions or problems? Okay. Okay, so last time we were looking at BreadthFirst Search and my PowerPoint was failing. So I'm going to quickly go through what we talked about before. So one point I was trying to make, not very successfully, was you're doing BreadthFirst Search. So imagine you've got this graph up here you're doing a BreadthFirst Search on. And BreadthFirst Search is trying to find the shortest path from some start vertex to every other vertex, if such a path exists. So we might find the shortest path from A to B is that yellow path. A to C might go that way. Then A to D might head that way, although we could have gone B to C, and then A to E might head that way. Now, what's the problem with an algorithm that reported those as the shortest paths? What's the problem with that report? Yes? Say what? There could be two, but we're satisfied with just one. But we wouldn't like if the algorithm came up with these particular shortest paths. Yeah?
Doesn't build a tree.
Right. When you add all the edges together, we combine all those edges together, we don't get a tree. So we don't just want to find the shortest paths, we want a shortest paths tree, or a BreadthFirst Search tree. And those colored edges all merged together don't give you a tree, because there's two ways to get to vertex D. So what we want to do is, it's always possible to find a shortest path tree. It would actually be a tree. So we could find A to B that way, A to C that way, A to D that way, and then A to E that way, and then we got a tree. And there it is. Put it in purple here. So we sort of combine all those together. So, if there's a shortest path from A to D goes a certain way, and the shortest path to E goes through D, we want the beginning of the path to be the same. And when that exists, when we have that situation, we can encode the tree. The reason we want a tree is because we can encode it very simply in a couple of arrays or a couple of hash maps. This is the previous array. This is the distance array. So each entry here, like the entry here says, in the shortest paths tree, what is the parent, the predecessor of B? And it's A. And what's the distance from B back to the root? And it's one edge. So our output, we want trees because we won't be able to describe the trees simply like that. And it's possible that some vertices could be uncoded. I mean, could be unreachable. So F is unreachable right there. No matter where you start from A, F is unreachable. And so it shows up in here as having no parent and being an infinite distance from the root. A, of course, has no parent, but it's a distance from the root. So that's how you can tell the difference between A and something that's unreachable. Okay, so that's what I struggled to do when I couldn't get the animation to work. And here's our BreadthFirst Search algorithm. And for BreadthFirst Search, unlike DepthFirst Search we use recursion. And in DepthFirst Search we use iteration with a queue. So what if we didn't want to use recursion in DepthFirst Search? It would make a nice symmetry if BreadthFirst Search was an algorithm that used a queue to control the order in which it looks at vertices that are visible, and DepthFirst Search uses a stack. I mean, DepthFirst Search does use a stack because the recursion is using the runtime stack. why not just write DepthFirst Search iteratively and create our own stack rather than relying on the runtime stack? Make a non-recursive DepthFirst Search. Can we do that? What would be the problems? You can make it work, but it's a little bit subtle. What are we expecting out of DepthFirst Search? Why do we do DepthFirst Search? Yeah.
We want a path.
Well, you said we want a path. That's not exactly right. It's not a path that we're after. Yes?
We're trying to get the lowest level first, so we're not quite sure how far we have to go to get to the lowest level.
You say the lowest level?
To the depth.
Well, it's still, there's a simpler answer to this, yeah.
We're just looking for a path down?
Generally, we don't do DepthFirst Search because we want to find a path. Yeah?
It's because I think it would mess up the post times.
It's the pre and post times
Yeah.
you're after, pretty
Yeah.
much. Sometimes you do an explore because you want to find out what's reachable. But the most use we've put to DepthFirst Search has been not to find paths. And if you think about it, we haven't created a DepthFirst Search tree. We've been interested in the pre and the post times. And so yes, you can take the DepthFirst Search algorithm and do it iteratively using a stack as your data structure, in much the same way that BreadthFirst Search uses a queue. But you have to be careful. It's not as straightforward as you might think because we want the pre and the post times to reflect what would happen if we were doing it recursively. And that's a detail that makes it not difficult to do DepthFirst Search iteratively with your own stack, but you have to think pretty hard to get it right. But having said that, DepthFirst Search, it's appealing to say DepthFirst Search uses a stack, so which means that the vertices that it sees first are the ones that are on the stack the least amount of time, so it tends to go deep, whereas BreadthFirst Search uses a queue, so the vertices it sees come off the queue are the ones that are closer to the root. So let's see how that works. So here's our algorithm. So the first thing that happens is we initialize our data structures over here. So we mark everything as being an infinite distance. We mark everything as having no pair. And then finally, we mark our root vertex. Notice the start vertex is a parameter to the thing, to BreadthFirst Search, unlike DepthFirst Search, which just chooses a start vertex arbitrarily. We mark our start vertex as being a distance of 0 from the root. So that's the initialization phase. Then we create a data structure. We create our queue here, and we add to the queue our start vertex. So that's priming the pump. So I'm going to use purple to indicate that a vertex is on the queue, and then when it comes off the queue, we'll change the color. All right, so let's work through the algorithm. We loop until the queue is empty. So as we discover new vertices we haven't seen before, we throw them on the queue. Every time through the loop, we pull one off the queue, and when the queue becomes empty, there are no more vertices to visit. We want to make sure that once an element comes off the queue, it never goes back on again. So let's see. We pull something off the queue, so there's only one thing to pull off. It's that guy, and we color it yellow, meaning it's now been dealt with. Then what do? We pulled A off the queue. What do we do? Right. We're looking at every edge out of U, every edge of the form UV, where U is the vertex we just pulled off. And we do this if the distance to V is infinite. So what does that mean? What does the distance to V being infinite mean? It means we haven't seen it yet, because as soon as we see it, we're going to enqueue it and set its distance set its distance to something finite. So that's how we avoid putting something on the queue twice. As soon as we see it, we take it off and adjust this stuff. So let's see what we do. We throw it on the queue. We're going to throw we'll throw B on the queue, and its distance becomes one more than the distance to U. So the distance to B will be one more than the distance to A. Okay, that makes sense. We've just followed an edge from some vertex U to another vertex V. We know the distance to V. We know the distance to U. The distance to V will be one more. And then we set the previous of V to be U, because we're following that edge from U to V. So we, let's see, okay, we're going to be up there. Okay, somewhere that happened too fast. Okay, so what I just did was I set the previous of B to be A, I set the distance to B to be one more than the distance to A, and I threw B on the Q. Okay, what happens next? Okay, we're going to deal with that edge from A to E. So we look over at E. It has an infinite distance. So we throw it on the Q and we set its previous and distance. Then what? Okay, we consider F and it goes on the Q and it gets adjusted here. Okay? Now, once we have set the distance, in this case to E, F, and B, will they ever change? Okay. The answer is no, but how do we know that? Yeah?
There's nothing smaller to replace it?
Say what?
There's nothing smaller to replace it?
Well, there's nothing smaller to replace it with, but what in the code keeps it from being replaced? Yeah?
You're only checking on it if its distance is already set to infinity?
Right. This is what stops it. The only way that any of those entries for A or B or E or F could change is if we execute this block right here, and we won't because the distance of B is now no longer infinite. Everything gets set once. So we're through with the edges out of U, which in this case is A. So now what happens? The loop continues, we pull B off, and we consider its edges. So there's an edge to C. And so now C is a distance of 2 because B was a distance of 1, and C's parent is B. And then we consider that one, but we don't do anything because its distance isn't infinite. Okay? Then, what happens now?
Go to possibility.
We'll take E off the Q, and we consider the edge out of it, and that's to an already visited thing. Now we'll take F off the Q, and it only points at a visited thing. So we pull C off the Q, and now there are a couple things to update. We update D to be a distance of 3 with a parent of C, and we update G to be a distance of 3 and its parent is C. And it just continues in this fashion. So eventually we're going to DQ D, and that'll update F, and then nothing else, everything that can be visited has been visited at this point. So we filled out the 2 arrays and we left on and visited them. So it just wasn't touched. So that's BreadthFirst Search, which I'm assuming is familiar. Yeah?
So I feel a little bit confused because this doesn't seem like BreadthFirst Search. This seems like a BreadthFirst traversal, right? There's no step that's like, oh, if this node is what we're looking for, then we're done. Or maybe I'm confused about what, the search.
Okay. So what she's expressing is, what are we searching for? It's called BreadthFirst Search, and yet there's not a goal. We don't have a goal in mind. Is that a fair summary?
Exactly.
Okay. So it's generating the BreadthFirst Search tree. So what do you think? Is it misnamed?
Oh, in that case, isn't DepthFirst Search also misnamed?
Yeah, DepthFirst Search wasn't necessarily searching for anything particular. It was just finding pre and post times. Yeah.
Maybe I'm wrong. It's kind of like an all-encompassing search. It finds like a bunch of different things rather than just one.
Right. It finds. He said it's an all-encompassing search. It finds the shortest path to everything. Now, what if you just cared about the shortest path to a particular vertex? How would you change this algorithm? Yeah?
So when you find it, you just break out of the loop and...
Right. As soon as you find, let's say we were searching for the shortest path to E. As soon as you set these values for E, you could just break out of the loop and return at that point. So it's easy to soup up. Yeah?
So that brings me to another question. It seems like since we're trying to find the shortest path, that it could be possible that the first path that we set for E isn't necessarily the shortest path, and so we would have to do the entire algorithm before we can determine that. Okay, so she's expressed a concern that maybe we shouldn't stop right away when we say incorporate D into this tree, because maybe there is yet a shorter path. But that would be true if there were weights on these edges.
how do we know that we're not going to find a shorter path to D? I mean, if we ran the algorithm to completion, we already argued that it's never going to update D at all. D is not going to change. So that's the nice thing about this algorithm. You don't have to reconsider any decisions. So yeah, you could have it stop early in certain circumstances.
But the solutions won't all be unique.
Well, okay, so is a binary search, is a BreadthFirst search tree unique? No, there could be other BreadthFirst searches. They would find the same distances. But the tree itself could be organized differently. It just depends on what? What determines the specific tree that you get?
The order in which you include events.
Yeah?
Your start node and the order you queue things.
Okay, so the start node is, if you change the start vertex, you're going to get different distances and everything. So we're assuming it's always the same start vertex. But what determins it is just the order in which you can make arbitrary decisions. So when we started at A, I considered the vertices in alphabetical order, B, E, F. That determined the order in which they were pushed on the queue, which determined the order in which I considered them. If I had put them in the opposite order, I would have followed different edges and gotten a different tree with the same distances. All right, so that's BreadthFirst Search. Yeah.
So, I'm sorry, you were saying that, to answer Sarah's question, these aren't weighted, so you could just stop if they were weighted.
Right, we'll talk about weighted when we got to consider the weights on the edges. In that case, we could not stop right away.
So you'd have to go through everything.
Yeah, you'd have to continue on. Couldn't necessarily stop just because you found the thing you're looking for. Yeah?
Just real quick, this is for only DAGs right now in this situation, right?
This is what?
For only for DAGs in this situation for now, or is this
this is
applicable to?
This works on directed, undirected, cyclic, acyclic. In fact, this isn't a DAG. Notice there's a cycle here. CGF is a cycle.
Oh yeah. Okay.
And it doesn't have to be directed either. BreadthFirst Search works fine. Essentially, if you a directed graph is an undirected graph is just a directed graph where edges come in pairs. If there's an edge from A to B, there's an edge from B to A. So you can have special algorithms that only work on undirected graphs, but if you've got an algorithm that works on a directed graph, it automatically works on the undirected ones. Any other questions? All right, let's analyze it. So we analyzed DepthFirst Search, and we'll be playing a similar game here. So I've sort of broken the algorithm down into bits, but initialize refers to that stuff at the top, where it's filling out the distance array of the previous array, initializing it. What's the complexity of that step? Again, assume we have V vertices and E edges. So how long does it take to fill in those arrays? Yes?
Oh,
Right, O of V, because the arrays are of length V. So there's our O of V term. Then we got to create the cube. Somebody else tell me, what's the cost of creating a cube? Yeah, constant time. It's basically an empty list. Okay? Then we got to throw S on the cube. Well, that's constant time as well. All right, now, over the life of the entire algorithm, so again, we've got this loop running. If we try to just count every statement by itself, it's going to be unclear how to do the counting, because a lot depends on how many edges are produced each time through, and whether or not this is true. So I want to consider over the life of the entire algorithm, how many times do we check if the queue is empty, in the worst case. Yeah? Okay, we do it V times, right? Once per vertex. At worst, one vertex will come off the queue every time through the loop, so it can't run more than V times. So it's O of V. Okay? Then, what about this DQ operation? How many times does it run? Yeah?
O of V.
Right, again, it's a constant time operation, but it runs V times. Then we've got to enumerate all the edges. So eventually, through all the iterations in this loop, and we're going to enumerate all the edges in the graph. Sometimes through the outer loop it'll be quick because there are not many edges. Another time it'll be longer because there's more edges. But what's the cost of enumerating all the edges? Okay, I'm hearing V, I heard E, I heard V plus E, but I didn't hear the right answer. V squared. Okay, so I still haven't heard the right answer. V times E? No, that's not good. Okay.
It depends on the representation.
It depends on the representation. If we got an adjacency matrix, it's V squared. Adjacency list, it's E plus V. So those answers were right, just not general enough. So I'm just going to say it's the cost of enumerating. We'll say the cost of enumerating the edges is whatever the cost of enumerating the edges is. And later on we'll plug in the specific representation. What about this test? How many times will we check whether the distance to a vertex is infinite? I heard O of E. Who could explain why that's correct, other than the proposer? Yeah.
You check every edge eventually.
Yeah. You only do that. You do that test every time you find an edge from from out of U. So you do that once per edge. And then, how many times will we run this stuff here? Yeah? Yeah, once per vertex. Each vertex gets dealt with once. And each of these is a constant time operation. So that's O of V as well. So there's our entire analysis. And if you add it all up, you get that. We got some O of V's, we got some O of E's, and we got the cost of enumerating the thing. And on a matrix, the cost of enumerating all the edges is V squared. So it simplifies to that. And on a list, the cost is V plus E. So it simplifies to that. So, just like DepthFirst Search, this is linear. The time it takes is proportional to the size of the data structure you're consuming. Can you do better? So I got the question, can you do better than linear? Yeah?
No, at minimum you have to examine every element.
Right. At a minimum, you've got to examine every piece of data in the representation. So that's the best you can do for these two representations. Okay, any other questions? Okay, now we're going to move on to a different problem. Shortest paths. So now we are going to add edges, add weights to our edges. And there are various ways to interpret them. They could be distances, they could be costs. Just depends on the application. Now we're interested in not finding the shortest path in the sense of fewest edges. We're trying to find shortest paths in the sense of least total cost. And we're going to make this assumption that there are no cycles of net negative cost. So what is a cycle of net negative cost? Yeah?
Each time you traverse the cycle, it'll cost less every time.
Right. So, yeah, so what he said was it's a cycle of edges such that when you go around the cycle, the total weight for going around is negative. So first of all, is there a cycle in this graph? Yeah, the FCG triangle. Is that a cycle of net negative cost?
No, it's positive 1.
Right, that's a 1. What is the problem with finding shortest paths if there's a cycle of net negative cost? Yeah.
Because you could traverse the cycle as many times as you want and continuously get shorter and shorter and shorter.
Right.
And there's no reason to stop because it would be.
So suppose you're trying to find the shortest path from A to C, but we change that -5 to a -7. What would be the shortest path? Would A to B to C be the shortest path? Cost 3? No, because I could go around CGFC, and now I'm down to 2. Is that the shortest path?
No, you just keep going.
No, I go around it again and again and again. I can make it as low as I want, and there's no limit. So there is no shortest path. So the problem isn't really well defined if you have cycles of net negative cost. So we're going to assume in all of our algorithms that there are no such things. All right? There's the answer for that graph. Notice we can encode previous and distance just like before. And the edges that are actually part of the paths are highlighted in yellow. And you look over here and see what the actual cost of the paths are. So from A to B is a cost of 2. From A to G is a cost of 5. From A to F is actually a cost of 0. You get that -5, which makes it cheaper. Okay? So there's a shortest path tree for that graph right there. Now, we talked about the problem with net negative cost. So let's just look at it in more detail. So there's where we change the -5 to the -7. Now we're violating our assumption, and the problem, as we know this, is there's no shortest path. The more times you go around, the lower the cost. So it's unclear, there's no way to put the distance there. Yep?
So, I know this is silly, but to me this seems like a cheapest path algorithm, not necessarily a shortest path algorithm. How do you like differentiate cheapest from shortest? Or this,
Okay, so she's asking about, she says this seems like a cheapest path out, a cheapest versus a shortest. Okay, so you don't like my choice of adjectives, it sounds like.
Sorry. I'm really sorry.
Right. Yeah, well, if these edges represent money, then yeah, that's cheapest. If they represent distances, it would be shortest. So yeah, I guess the answer is there's no one adjective that works, so we'll just call it shortest.
Okay. I was just thinking, like, if it's -5 before, you said the shortest path from A to F is to go A, B, C, G, and then F. But to me, the shortest path looks like it's just from A to F.
Okay.
Right? But I'm over it. I'm good.
Okay. Yes.
It almost seems like, what kind of representation would have negative weights?
Okay, where would negative weights come from? You got an idea?
I think I noticed a bug in the slides.
Huh? Where's the button?
D shouldn't be 4, it shouldn't be ~2 or -infinity, because you can just write it.
No, that's true. In fact, D and H, and E for that matter, should all be question marks.
But B and A are good.
B and A are good. Yeah?
Well, first as an example for when you have negative weights, take like a pathfinding algorithm in like a game. If there was some like terrain type that sped up units, then that would be considered a negative cost because they can move faster through that.
Okay.
As an example.
So for possible to move from A to B to C in a game and you got a net speed up every time around,
Right.
right, you could get arbitrarily fast by circling it.
Right.
There's a problem in the book that I sometimes assign that has to do with using graphs to model currency exchanges. And so imagine that you've got dollars and you want to change them into euros, and then you change the euros into pesos, and then you change the pesos back into dollars. Usually when you do that, you end up with less money than you started with. But if you follow the currency exchange markets really fast, or really carefully, you might find an instant in which it's possible to go around that cycle and make money. And if you can do that, then the more times you go around it before the exchange rates change, the richer you get. It's hard to explain how that turns into a negative edge, but that's an example of you're trying to maximize your profit. This is more like a cycle of positive weight. You're trying to find the longest path, the most valuable path through it, and there's not one, because the more times you can spin that circle, the better it gets. Yeah.
Is it possible to have a negative distance? So say you have this table like this, and that 4 from F to C was like 10, so that it's no longer
Sure.
net negative. F would then be 2 to the 3 -2 to get
Sure.
an estimate. Is that possible?
Okay, yeah, you can have a negative cost to get something.
Okay.
Yeah. So if you're thinking in terms of, distances to cities, or changes in elevation, you're modeling the real world. You're not going to get, cycles of net negative cost, right? If you hike from here to there to back again, that's going to be 0 net altitude gain. You'd be surprised if you lost altitude by going in a cycle. But other things you can model with graphs, negative edges.
How about voltages?
Come. Okay. Well, yeah, he's suggesting voltages. We could come up with examples, but just there are negative edges, negative weights that come up in nature, and there can be negative cycles as well. Now, suppose we change the problem. So instead of asking for shortest path and saying we're assuming there are no cycles of net negative cost, we could ask for the shortest path that does not include a cycle. Okay? So if we took this graph, which has a negative cycle, and didn't ask for the shortest path, we just want the shortest path that does not include a cycle, suddenly the problem is well formed. Right? Now, the shortest path to F is just A to B to C to G to F. That's the best you can do. You end up with -2. Because you're not allowed, we want the shortest path that does not involve a cycle, so you're ruling out going around the cycle. The reason we don't pose the problem that way, the reason we don't, instead of relying on the algorithm to avoid cycles, we're saying the graph does not have cycles to start with. This more generalized problem is NP complete. We'll talk about that later in the semester, but what it means is it's very unlikely there's an efficient way to solve that problem. So that's why we are assuming that the cycles aren't there to start. Now, what if you're interested in a longest path algorithm? Is there anything special about shortest?
No.
Yeah, we could easily take a shortest path algorithm and turn it into a longest path algorithm. How would we do that? Well, it'd be an easy transformation. He said switch less than to greater than. That's one way to do it. You sort of reverse the sense of all the comparisons. That's another way we could do it. Use the exact same algorithm, just modify the input. Yeah.
We can flip the value around.
You just flip the sign on all the weights.
Yeah.
So if you negate all the weights and continue looking for the shortest path, then the shortest path will be the longest path in the original graph. But if you have a graph and you're asking to find the longest path, what would the restriction be on that graph before you negate the edges? Yeah?
No cycles.
No cycles of positive weight. Yeah. Okay. Now, we've just posed the problem. Let's look at approaches to finding shortest paths. BreadthFirst Search.
Did you Hamiltonian path in that case?
Get the right one here. Shortest path is right there. Not going to do this to me again, is it? Sorry about this. Let's take a break. A few minutes, I'm going to figure this out. finding shortest paths. One is the most general. It'll work on any graph that doesn't have a cycle of net negative cost. Then there's one that'll work on a DAG. And then there's one that'll work if there are no negative edges. So you'd expect the more general one to be the least efficient, and the other two specialized ones to be more efficient, and that would be true. But what all of them have in common is they all use an update operation, or the same update operation. So when you update an edge, you're like you would update, say, the edge from B to C. So you need to know about the edge. You have to know its starting vertex, its ending vertex, and its weight. And so this is the update operation on an edge. It says that if the distance to V, so V is the endpoint. So if we're talking about that edge from B to C, V would be C. If the distance to V is greater than the distance of U plus W, then you update the distance to V, and you update the previous to V. So what's going on here? What's the key idea behind the update operation? Okay.
If you find a better path, then update it.
Okay. So this is saying that you're examining that edge from U to V to W, and you notice that if we already know a way to get to U, that's distance to U. So if the way we know to get to U plus W is better than the way we know to get to V, then whatever way we're getting to V right now is bad. We should instead go through U and then follow the edge from U to V. So if you found a better way, update previous and distance. Yeah?
So what happens if it's still in the queue?
He said if it's still in the queue, there's no queue here. We're not talking about a specific algorithm, we're just talking about update operation. Okay? Yeah?
What is the relationship between U, V, and W?
U, V, and W is an edge from U to V of weight W.
Okay.
So U, take that edge from B to C. U would be B, V would be C, W would be 1. So UVW describes a weighted edge. So the idea is all these algorithms, the only way they modify previous and distance is via the update operation. So they differ in how they choose which edges to update. So the less efficient one just sort of updates in a very non-clever fashion, just sort of brute force. It just updates edges over and over again. The other two algorithms are more selective about what edges they update and when they do the update. So they're faster because they do fewer updates. So the idea is each time you update, each time update makes a change, you're getting closer to the actual solution. If you ever get into a situation where your previous and distance arrays are such that no matter what edge you update, nothing changes, you have found your answer. So you start with a completely, every distance is infinite except to the root, and every previous is null. And you update, and if you do that enough times to enough edges, you'll eventually get to the right answer. You won't get stuck in the wrong answer. There's always a way to move forward. Yeah?
How do you know when you've done enough updates?
Okay, so he's asking, how do you know when you've done enough updates? Well, that's when we have to talk about the specific algorithms. Right? Each algorithm decides what updates to do and when to call it quits. They do it in different ways. But what they have in common is the update operation. So I'm still not ready to talk about a specific algorithm, but suppose we just for the heck of it, let's update these edges in that order. So what's going to happen, this will be our initial state for all our algorithms. Everything's infinite except for the start vertex. So what's going to be the result? What will change about previous and distance if we update that edge AF of 4? A to F of weight 4. Yes?
F previous becomes A, and
All right.
distance becomes 4.
Okay, so F's previous becomes A and its distance becomes 4. And the reason that is because the current distance to F is infinite. And the distance to A is 0. So we add the 0 and the 4, we get 4. That's better than infinity. So we do that update. And we get the update there. Now suppose we update CG2. So we got an edge from C to G of weight 2. Yeah?
So we go to G, we update pre with C, and then we update dist with infinity plus 2.
Well, okay. So it's actually simpler than what he just said.
We just set G.
What's that?
We just set G's previous to C.
Well, what's the first thing that we'll do? What's the first thing the update operation does?
Check the distance.
Checks the distance. Okay, what's the distance to V? Infinity. What's the distance to U? What's infinity plus, what is W in this case? 2. What's infinity plus 2?
Infinity.
Is infinity greater than infinity? No. So we don't change anything at all. So we sort of wasted our time with that update operation. Incidentally, I noticed in last week's CATIS problem that there were a lot of students who were having this problem where infinity plus something was not infinity, it was negative. So I know a lot of students caught that. There may be some that didn't. That if they were using, say, max n for infinity, when you added something to max n, it suddenly becomes a negative number. So you got to be careful when you're using infinities in programs. Okay, what happens if we update FE1 to the edge from F to E? What will change? Yeah, we'll get the 5. Because right now the distance from F to E, the distance to E from the root is infinite. But the distance from A to F is 4. And the cost of going from F to E is 1, so we add that up, we get 5. So it changes that entry. Now, what happens when we do that update? AE3. Yeah? Okay?
E gets updated to 3.
Yeah, E gets updated to 3. We know a way to get there costs 5, but getting there via 3 is better, and so we're going to change E's distance to 3, but also its parent to A. So we did 4 updates, and we ended up here. Now, how could we have accomplished the same thing doing only 2 updates? Which updates were a waste of time? Yeah?
The 2 in the middle were erased.
Right, the 2 in the middle. This one here, nothing changed at all. This one here, something changed, but then we found a better way. So if we had known that was going to happen, we could have gotten to the same point by just doing 1 and 4. So that's what an algorithm is going to do, is try to figure out the right sequence of updates to do so that you do as few as possible. Now, is there a perfect order? Suppose you knew in advance what the answer was. Someone asked you, what's the shortest sequence of updates I can do to get the right answer? And you sort of go to the side and solve the problem, and then report back what the right sequence of updates is. So what would be the right sequence here? I've highlighted the solution in yellow. Yeah.
So you start wherever you're going to start to calculate the shortest path, and then you check all the edges leading out of that, and then you continue checking along the shortest of those paths that lead out of that.
When you say check all the edges out,
check the weights of all the edges and update them, and then continue updating from the vertices that.
Okay, so I think you're trying to describe Dijkstra's algorithm to me, maybe, or you're describing something like Dijkstra's algorithm. I don't want to update all the edges out of A. I can be more clever than that. And remember, this is not. I'm not asking you to describe an algorithm that will figure out the optimal. Any algorithm, most algorithms are not going to find the optimal series of updates. But you get to look at the graph. Yeah.
Cheapest out of A and follow that.
Check for the cheapest out of A and follow that. No, there's a simpler way to put it. Yeah.
You just update A to B. You know the answer, right? So
Right. You update the edge from A to B first. It turns out the only edges you have to update are the yellow ones. Okay? Why don't you have to run update on anything else? Yeah?
Is it because you hit all the nodes you can, just taking that one?
Yeah, the yellow one is the answer. We know the shortest way to get from A to B is that yellow edge. Because, I've told you, you can solve the problem and then go back and figure out what the optimal updates would have been. No need to bother with the edge from A to E. It doesn't contribute to the answer. It'd be a waste of time to update that edge because it's just going to get overruled later. So all you have to do is update the yellow edges. Done. In what order should you update the yellow edges? You start, you do the ones that lead directly out of A. You sort of do it in BreadthFirst order. So you would update the one out of A, and then you'd update the one out of B, and then you'd update these two in either order. Just make sure you update all the edge in before you update any edges out. You update the yellow edges in before you update the yellow edges out. If you do it in that order, you're going to end up with your solution. So if you could somehow divine which edges are yellow, then you could report what the optimal series of updates are.
Aren't the yellow arrows create a DAG?
Yeah, the yellow, he says, don't the yellow arrows create a DAG? Yes, in fact, they create a tree. It's stronger than that. So the point of this isn't that the algorithms are not going to discover, generally speaking, the optimal order of updates. But an optimal order exists. And it's possible to determine the optimal order. Now, suppose someone said, okay, here's a graph, forget about the yellow edges. You can see the yellow edges, they can't. Suppose someone said, if you do these update operations in this order, you will obtain the shortest path tree. How could you check? How could you check that the updates they're proposing to do will in fact yield the correct answer? So they give you a list of updates. You've got to say whether or not that's going to work. Yeah?
You have to have an edge from U to V for each vertex that's possible to reach from.
Okay, so any answer you give me has got to use the word yellow.
Okay. You need a yellow edge for any vertices that you could reach from the root?
No, that's not getting right at it. What has to be true about their list of updates?
Each yellow edge would have to be an update in their list.
Okay, that's certainly true. Assuming there aren't ties, so let's assume there are not multiple ways to solve the problem. Your yellow updates, you have a list of yellow updates to do. Those updates had better show up in their list. If they're not updating a yellow edge, they're not going to find the optimal solution. But there's something stronger you got to answer. Yeah.
Well, isn't that alright after this array?
No, this part doesn't matter.
Oh, okay.
The question is what's the other check you have to do? Yeah.
If their list of updates is optimal, then it won't have any updates.
Well, certainly, if their list is optimal, it'll match yours. But we're not asking whether their list is optimal. We're just asking, does it work? Yeah.
It needs to be in the right order.
It needs to be in the right order. So if your list is a sublist of theirs, then their list of their sequence of updates will work. So, as long as you can take their list, throw out a bunch of updates, and have your list left in the same order, then their updates will solve the problem. Yeah.
I'm kind of confused because I feel like in order to optimize the shortest path, we need to look at every path.
Okay, so he's saying that to find the shortest path, we've got to look at every path in the graph. What do you think of that? Do we need to look at every path in the graph in order to find the shortest path?
Or else how do we know that the path we have is the shortest if we haven't considered all of them?
Okay. Otherwise, if you haven't looked at some of the paths, how do you know it's the shortest? Now, just realized I don't have my pen with me, apparently. Oh, there it is. So that's a good question. We're trying to find the shortest path. Do we need to look at every path? No? Let's see. I'm going to draw a graph here. let's see.
It's not up.
No. Thank you. Okay, let me draw this graph here. So I'm going to have a vertex here, and a vertex here, and a vertex here, and a vertex here. And then I'm going to do it I have lots of vertices. Go like that, and then the edge pattern is going to be like this. You get the idea? To that diamond pattern. How many paths are there through this graph? Suppose there are n of these little diamond things. How many paths are there from the start vertex to the last, from the sink, I'm sorry, from the source to the sink?
4n.
2 to the end.
2 to the end. Okay? How many ways are there to get from there to there? 2. To get from here to here, it's 2 times 2. Because you could go, let's look at the ways to get to here. You could go like this, or you could go like this, that's 2. You could go like this, that's 3. You could go like this, that's 4. Then how many to go 3 hops? 2 times 2 times 2, 8. So that means if we have n of these diamonds, there are 2 to the end paths through the graph. If he suggested that you have to look at every path in order to find the shortest one, what would that say about the complexity of any shortest path algorithm? Yeah?
To clarify, I said you had to look at the edge.
No, you didn't.
Okay, I meant edge.
Okay. Yes, you certainly have to look at every edge. But it was such a good question, I'm going to keep answering it. What's the fundamental problem with looking at every edge? I mean, every path. Yeah.
It would be really expensive because there's a lot of checks.
Right, there's 2 to the end paths, so if you had to look at every path, what lower bound could you put on the complexity of the shortest path algorithm? Right, it would be, any algorithm would be omega of 2 to the n. So we can't afford to look at every path. I think you said that. We could go back to the tape. But I'm glad either you asked it or I misheard it, because that's a good thing to talk about. Okay. Yeah, you got to look at every edge. Well, maybe not even. Turns out you don't have to look at. Turns out you don't look at those edges right there. They turn out not to be relevant. Okay. So we decided that if someone proposed some order in which to do updates, you could easily check whether that order is going to yield the correct answer by making sure that your list of yellow updates is a sublist of their bigger list of updates. Okay? Now, why am I raising this question? What's it have to do with algorithms for shortest paths? Okay?
The lower bound of the number of updates you have to do.
Well, there's certainly a lower bound on the updates. The lower bound is we got to do at least v minus 1 updates. But the point is, there are 3 algorithms. What these algorithms all do is decide in what updates to do in what order. So in order to convince ourselves these algorithms are correct, we just got to convince ourselves that the updates that they do are a super list of our optimal yellow list. So an algorithm could spend 10 minutes updating edges at random, wasting time. The point is, it's not going to get stuck in such a situation it won't be able to find the answer. It's just wasting time. Update, 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 doesn't matter as long as it eventually does those yellow updates in the right order. So it can maybe update A to B after half an hour. Well, that's okay as long as after updating A to B, it eventually updates B to C. And after updating B to C, it eventually updates these edges. So, this is just talking about what I've been talking about all along. That you want to update the yellow edges in a proper order. So that's updating A, B, then we update B, C, then we update C, D, D, H, C, G, G, F, F, E. So just by doing those updates, you reach the solution. Now to do that, we had to know what the answer was to start with. But if the algorithm could somehow figure that out on the fly, be good. So, can you think of a brute force way of doing updates that guarantees that our yellow list of updates is a sublist of the updates actually done by the algorithm? Okay?
I mean, a brute force way would just be to step through each child with each node, check, do it, update, then move to each child and do their update.
Okay? There's even a simpler way to describe that. Yeah?
So like if you do AB, then the next one you update is B to another node. So you like.
Well, again, you're being too clever to call it brute force. Yeah?
I think our original BreadthFirst Search algorithm did it, except it didn't take into account the cycles. So if we just cut off cycles from...
Well, but our BreadthFirst Search algorithm isn't, by not paying attention to weights, it's not necessarily going to do the updates in the right order. For example, it would update that edge from A to E. Well, that's not the right example, but it's not guaranteed to work in the right order. Yeah?
Would backtracking be a brute force?
You don't have to backtrack. Yeah?
Explore, use Explore,
Do what?
use Explore.
No, not use Explore. Yeah?
Just update everything.
Yeah. Update every edge. Okay? What does that guarantee if we update every edge?
The right ones.
It doesn't guarantee those yellow edges were, it guarantees the yellow edges were all updated because all edges are updated, but were they updated in the right order? But at a minimum, what do you know? How much of your yellow list have you dealt with if you update all the edges? No. Remember, my yellow list has to be a sublist of the algorithm's list. We update every edge once. What can you say about my yellow list? Yeah.
That you've at least done the first
I at least did the first edge in my yellow list. Right? It happened somewhere. So then what do we do? Update them all again. What does that guarantee? We did the second edge in my list, and it came after doing the first edge in my list, because we know the first edge in my list happened in the first batch of updates. And then we do a second batch of updates, and now the second one is guaranteed to have been updated. And we did a bunch of other stuff, but at least we've got those first two edges right. Then what do? Do it again. Now the third edge in my schedule happened at the right time. So how many times do you have to do this for guaranteed that we've done all the yellow updates in the right order?
V
V minus 1 times.
V minus 1 times, right. At most. V minus 1 times, because that's, we're building a tree, and that's the most number of edges we could have in a tree. Now, how could we stop early? I mean, it may be that you get lucky. Maybe that first update, it just happened to update the edges in the right order. Yeah?
So the first one, you know that only A is going to matter, or all edges going out of A. So maybe every time you could just keep track of the subgraph, the subtree, and then only update all the edges coming from nodes in that subtree. Okay, well again,
you're proposing, you're getting a little more clever than I'm going to get. What would be a simple way to tell after you've updated every edge that you can stop? Yeah?
None of the distances change.
Right, if nothing changes. If you do a general update every edge and nothing changes, there's no point in another update. Nothing's going to change that time either. Now, here's a tricky question. Looking at what the solution is, can you tell me how many updates before anything changes? What's the longest sequence of updates you can do before something stops changing for this particular graph? You can do better than 8. Yeah?
B plus E times B minus 1 times.
Well, you have to look at this specific graph. The answer is a number. I got 7. What do you got? Okay. Well, let's see. It turns out that it's guaranteed to find the correct answer if it does general update once for each edge in the longest path. So the longest path in this is 1, 2, 3, 4, 5. Right? So you can do it in 6. The 6th time, things are guaranteed to stop changing for this. And you could puzzle about why that is. It's just the first update is guaranteed to do AB. The second update will do BC, and that BC has to have come after AB because that happened in the first update. What can you say about the third update? It's guaranteed to update this edge and that edge. Does the order in which you update these two matter? They're dependent. So that means you've dealt with this much of the tree. The next update, you've dealt with all the paths of link 4. The 5th update, you've dealt with the paths of link 5. And the 6th update is we just know from looking at this, it's not going to update anything. So you could stop after 2 updates if you get really lucky. But you can't take more than 6. And the 6th one is nothing's going to change. So that algorithm is called the Bellman-Ford algorithm. We don't know what the perfect order is, so we just update all the edges once and again until you find the shortest path. Now, what I've left out of the algorithm is the optimization, which would say if nothing changed, you can break the loop. That's what that is for. So this is our first algorithm. It's definitely brute force, the definition of brute force, but it is simple. We initialize our data structure. In fact, all our algorithms have that in common. And then we just update all the edges a bunch of times. At most v-1 times, we can stop early. So it'll take at least 2 repetitions, at most v-1. Bellman-Ford. It'll work on any graph as long as there's not a cycle of net negative points. What would happen if you fed this thing? Suppose you weren't stopping when you've done v-1 times. Suppose you just stopped when things stopped changing. What would happen if you fed Bellman-Ford a cycle of a graph with a negative cycle? Yeah, it would keep changing every iteration because you keep following the cycle and finding better and better ways to get places. All right. So there's the algorithm. Any questions I could answer about it before we analyze it? Yeah?
Was the optimization added later? Like, when you refer to this algorithm, does it ignore, do people not consider, like, the optimization as part of it? Or is
No, it wasn't like it was added later. It's just, like right now we're doing a worst case analysis, so we're going to ignore the optimization. But it's easy enough to add in. Okay, let's analyze. So what's the cost of that initialization block up there? Filling in the previous and the distance arrays. Seems like we've seen that before. That's just O of V. What's the complexity of this loop right here? One run of that for each loop. Yeah?
The number of edges.
Okay. So update is called once per edge. What's another cost of that loop, of that for each loop? What do you have to do besides update each edge?
You have to repeat it.
No, I'm not talking. I just want one call of the for each loop, one run of the for each loop. There's a cost beyond updating each edge. Yeah?
just the cost of visiting each edge?
It's the cost of finding all the edges. Right? That always shows up. In the life of that for each loop, we've got to find all the edges. And so it'll be whatever the cost of enumerating the edges is for our data structure, plus E. And what do we get now if we want the total? Do we just add them together? O of V plus O of U plus O of E? What's missing? Okay.
The repeat of V times.
v minus 1 times, so we really need to multiply this cost by v minus 1, or we're doing big O, so we just multiply by v. So there's our total. O of v plus O of v times the cost of enumerating plus O of v times the cost of updating each edge. Now, how can we simplify that expression?
What's in there?
Is this term guaranteed to be no bigger than that term? Yeah, this is O of v, this is O of v times something else, so we can get rid of that. What about O of v times z compared to that? Is either of those ones redundant? I mean, you think of the v's as sort of canceling out. How does e compare to the cost of enumerating? It's got the cost of enumerating has to be at least as big as the number of edges because you've got to do something for each edge. So we can just say that's that. So this simplifies to that in bigger terms. And then we just use for a matrix, it's O of v cubed. The cost of enumerating is v squared. So it's a v cubed algorithm. For a list, it's O of v squared plus ve. So it's an expensive algorithm, especially on the matrix there. Okay, not linear, but easy to describe, easy to understand. Okay. Any last questions before we look at our next one? Okay, now, can we do better if we got a DAG? So I've changed the graph so that triangle right there isn't a cycle anymore. So it's a DAG. Yeah?
Question on the previous one.
Okay, question on the previous one, yeah.
Couldn't we do better by just extracting all the edges out first, and then we don't have to enumerate all the vertices and all the edges? We can just
Okay.
through all the edges.
All right, so he makes a good point. Let's go back. We really only have to do this once, right? Because we could extract all the edges, put them in a set, and then iterate over it. So how would that change our analysis?
So it'd be the same for the, it'd just be VE then.
So we pay that cost once. We'd still be O of V. We would do this cost once, and this would be of O of E times V. So we'd end up with O of the new plus O of the E. So how would that play out for a matrix?
O of E plus V.
It would be O of E new plus VE, so this would be V squared. So we get V squared plus O of V times E. If it's a dense graph, we'd get a V cubed term there. It improves the algorithm if you generate the edges once. Imagine the case where you have an adjacency matrix, a huge adjacency matrix with only a few edges in it. It's extremely expensive to find the edges, so just do it once, save the edges in a set, and that speeds up everything else. I'll leave that as an exercise too. That's a good observation. Okay, now we want to solve the problem on a DAG. Don't have to worry about cycles, negative cost or otherwise. We still need to have an algorithm that will, whatever it does, it needs, if we look at the updates it does, it needs to be updating those yellow edges in the right order. People always ask me what this algorithm is called. There's Bellman-Ford, which we just saw. There's Dijkstra's, which we'll look at next time. And there's this one, which as far as I know doesn't have a name, so we'll call it the autosync algorithm. Yeah. Okay, so the trick is to topologically sort. Now, I said this is the autosync algorithm. What would you have to change about the autosync problem to solve it with this algorithm?
Change the concept of vertices to edges.
Right. What he said was, essentially, in the autosync problem, the costs were associated with the vertices. So to use a shortest path algorithm, we would have to take the cost on the vertex and turn it into cost on the edges. So if you've got 3 edges coming into a vertex whose total is 5, you would just you put the total on those 3 edges coming into it. So you modify your graph that way, then you can run a shortest path algorithm on it. Okay, so the trick is to linearize the DAG and then update the edges in linear order, in linearized order. Now, why will that serve to do all the yellow updates in the right order?
Because the yellow updates.
You said because they're sorted. And what this doesn't say is after you linearize, really what you start with is your root vertex A. And then, so you find it in the linear order, and then you just proceed to the end. So if we linearize this DAG here, what do we update first? What edge do we update first? Which edges do we update first? Yeah? The ones coming out of A. So we'd update A to B, A to F, and A to E in some order, right? Now, if we were all seeing, we would know just to update A to B, but we're not, so we update all three of those edges. Okay? So we dealt with the first edge. Our first yellow edge got done in the right spot. Now, what would be updated next?
B.
Either B or E, depending on...
Well, it couldn't be E because it's lower, right? In the
Well, if you do a topological sort...
top. We're still on the sort. I was
you're right. You're
being
right.
sorted because E is dependent on everything.
Yeah, you're right. I forgot about the edge coming in. So the next one would have to be B. So you'd update all the edges out of B, which would pick up that edge from B to C. So now we've done A to B in the first batch, B to C in the next batch. What comes next?
G.
Either G or D would come next. If you do, wait, we've done A, we've done B, then would come C. So you'd update these yellow edges both. Then you'd either do D or G. So maybe you get that edge next. The next one would be G, and you get that edge there. And then later on you get F. The point is, you end up updating every edge. But if you do that in linear order, the yellow edges get updated in the correct order with one pass. So you just update the edges out of the vertices in linear order. And that's the algorithm of the DAG. Okay, so let's look at it. There's one way to linearize this DAG. Maybe I would come first, and then A, B, C, D, H, G, F, E. And this is one possible order in which the edges are considered. So we get the ones out of I first, then the ones out of A, and then the ones out of B, C, D, G, so on. Notice the yellow edges get considered in a correct order. Do this one first, that one second, these two third and fourth, the order doesn't matter, and so on. So unlike, one extreme, we got Bellman Ford, which is updating everything over and over again, hoping to luck into the sequence. Here we did the first try, as long as we linearize. How could you have known that this algorithm would require a topological sort before I told you?
DAG.
Because it's a DAG. Yeah. So, what's the complexity of this? Yeah?
E plus C.
Okay, so the cost of linearizing is linear. It's proportional to the size of the data structure. So it's cost of enumerating. And then, what about dealing with the vertices? Updating each edge. What's the cost of updating each edge? What's the cost of updating a single edge?
Constant.
That's constant. What's the cost of updating all the edges?
Constant times even.
All right, you've got to update each edge, which is constant time, but you've got to find the edges. So that's the cost of enumerating. So that step is also the cost of enumerating. So in a matrix, this DAG algorithm is b squared, linear time, and on the list. It's just proportional to the cost of consuming the data structure. Best you can do. So there we saw two extremes. We got the DAG on one side, which is very simple but only works on DAGs. We got Bellman Ford on the other, which is general but is really inefficient. In the middle, we have Dijkstra's algorithm, which is fast, not quite linear, but it's fast, and it But it does have a restriction, no negative edges. Not just no negative cycles, no negative edges at all. Right? We will pick up with that next time.